At first glance, Starship's stainless steel body might not seem all that impressive. I mean, it's basically a giant metal cylinder. But making a giant cylinder look smooth, sleek, and shiny, while also surviving launch, the vacuum of space, re-entry, and landing again, is a lot harder than it sounds. And one of the biggest reasons modern starships look so much cleaner and more refined than those early soda can-looking prototypes comes down to something surprisingly simple: welding. In just a few years, the difference is incredible. Today's starships have cleaner lines, smoother surfaces, stronger structures, and far fewer visible imperfections. It's one of those improvements that's easy to miss until you compare the vehicles side by side. So how did SpaceX get so much better at welding in such a short amount of time? Well, that's actually a pretty fascinating story. Back during the earliest Starship days, the infamous water tower era, the company relied heavily on Flux-Cored Arc Welding, or FCAW. It works by feeding a tubular wire electrode through a welding gun. Inside that wire is a special flux-filled core. When the wire touches the metal being welded, an electric arc forms between the wire and the workpiece. The intense heat generated by the arc melts both the wire and the base metal, allowing them to fuse together as they cool and solidify. Because the wire itself melts and becomes part of the finished weld, FCAW is known as a consumable electrode process. The flux inside the wire plays a crucial role as well. It shields the molten metal from contamination and helps create a stable, durable weld. Without that protection, oxygen and nitrogen in the atmosphere could react with the hot metal and weaken the joint. The reason flux-core welding became so popular across many industries is simple. It's fast, productive, and doesn't require overly complicated equipment. And for the early Starship program, those advantages were extremely valuable. SpaceX was trying to build enormous stainless steel structures as quickly as possible while constantly iterating on new designs. At the time, speed often mattered more than perfection. But FCAW came with trade-offs. While it allowed rapid construction, it wasn't exactly known for producing beautiful aerospace-grade welds. The process generated significant spatter, larger heat-affected zones, and more distortion than some of the advanced welding techniques SpaceX would later adopt. Every time heat entered the stainless steel, the material expanded and contracted as it cooled, making it harder to maintain precise shapes and dimensions. The result was a rocket that looked, well, a little rough around the edges. Those early weld seams were thick, highly visible, and sometimes inconsistent. In some cases, they could introduce structural weaknesses or require additional rework. If you've ever looked at photos of SN1, SN2, or the earliest Starship prototypes and thought they resembled a giant science project assembled in a hurry, you're not entirely wrong. After that, SpaceX started improving the process. The company switched to 304L stainless steel, which handled welding better and performed well at extremely low temperatures. They also adopted more advanced welding techniques, like TIP TIG welding, which allowed for deeper penetration, cleaner seams, less warping, and stronger joints. At the same time, they began using larger steel sections for each ring, reducing the total number of welds needed in the first place, because the best weld is often the one you don't have to make. Another major innovation was something called planishing. After welding, a massive, custom-built machine literally hammers and compresses the weld area. It sounds brutal, but the process restores strength in the metal, smooths out imperfections, and helps eliminate the visible scars left behind by welding. That's one reason newer starships look dramatically sleeker than the prototypes from just a few years ago. Then SpaceX appears to have taken its welding technology to another level. Laser welding has become an increasingly important part of production. Unlike traditional welding methods, which spread heat over a relatively large area, laser welders focus enormous amounts of energy into an incredibly small spot. The result is a deep, narrow weld with far less heat input, less distortion, and a much cleaner finish. Ironically, when SpaceX engineers first encountered handheld laser welders, they weren't immediately convinced. The machines looked more like something you'd find in a sci-fi movie or a YouTube safety warning video than a serious manufacturing tool. That skepticism didn't last long. The team initially experimented with the technology for tack welding, the small temporary welds used to hold parts in position before final assembly. Starship's stainless steel sections require extremely long weld seams, and traditional TIG tack welds often created larger bumps and imperfections than engineers wanted. Handheld lasers produced much smaller and cleaner tack welds almost immediately, making them useful from day one. But the real surprise came when engineers pushed the process further. As testing continued, they discovered the lasers could create full penetration welds through stainless steel while leaving behind only a tiny weld bead on the surface. That challenged one of the oldest assumptions in welding, that a strong weld should look big and bulky. Suddenly, SpaceX was producing welds that looked smaller, but were every bit as strong. The technology took another major leap forward when handheld laser systems began incorporating wire feeders. Early versions relied on autogenous welding, meaning no filler material was added. That made the process extremely sensitive because even slight variations in movement could affect weld quality. Once filler wire was introduced, the wire naturally guided the welding torch along the joint, making the process far more stable and repeatable. That was the moment handheld laser welding stopped being an interesting experiment and started becoming a serious production tool. And perhaps the biggest advantage was something every Starship engineer desperately wanted: less warping. Traditional MIG and TIG welding dumps large amounts of heat into metal. As the steel heats up and cools down, it expands and contracts, causing distortion. That's annoying when you're building a car. It's a much bigger problem when you're building a 50-meter-tall rocket that has to survive launch, reentry, and repeated flights. Laser welding dramatically reduces that issue by concentrating heat into a tiny area. Less heat means less movement in the metal, which means the finished structure stays much closer to its intended shape. In fact, some of SpaceX's tests produced results that would make any welding engineer smile. Certain laser-welded joints proved so strong that the surrounding stainless steel failed before the weld itself. In the welding world, that's about as good as it gets. It means the joint isn't the weak point anymore. The metal around it is. And that's when it became clear that those tiny laser welds weren't just cleaner, they were helping make Starship stronger, lighter, and easier to build all at the same time. After SpaceX got the technique down, the next step is to automate on a massive scale. Robotic welders, custom manufacturing equipment, and highly specialized tooling allow Starbase to produce vehicles much faster and with greater consistency than before. Every weld is inspected using advanced techniques like X-rays, ultrasound scans, and dye penetrant testing to catch defects before they become problems. The result is a rocket that is smoother, lighter, stronger, and faster to build than anything SpaceX was producing just a few years ago. And finally, there's one more piece of the Starship puzzle that's worth talking about: the Raptor engine itself. Because while Starship gets most of the attention, Raptor is really the beating heart of the entire program. Without it, Starship is basically the world's most expensive stainless steel water tower. And building these engines is incredibly difficult. In fact, the precision requirements are so extreme that early Raptor production relied heavily on manual welding for some of its most critical components. Automated systems simply couldn't hit the tolerances SpaceX needed. Welders who worked on the program have described situations where a tiny imperfection could potentially ruin a component worth hundreds of thousands or even millions of dollars. No pressure, right? Part of the challenge comes from the materials involved. Raptor uses advanced superalloys, including SpaceX's SX500 alloy family, which are designed to survive some of the harshest conditions imaginable. Inside the engine's oxygen-rich turbopumps, pressures can reach roughly 800 atmospheres. That's not just high pressure. That's the kind of pressure that makes engineers wake up at 3 a.m. wondering if they forgot something. These alloys are descendants of Inconel-based materials, which are famous for being incredibly strong at high temperatures, while also being notoriously difficult to manufacture. Inconel work hardens rapidly, meaning that after machining it once, it often becomes even tougher to machine again. But that difficulty comes with huge benefits. At extreme temperatures, these alloys form protective oxide layers that help prevent corrosion and allow components to maintain their strength where many other metals would begin to deform or fail. To create many of Raptor's most complicated components, SpaceX also relies on advanced foundry casting techniques. Molten metal is poured into highly detailed molds, allowing engineers to create intricate shapes that would be difficult, expensive, or sometimes impossible to machine from solid blocks of metal. Components like manifolds and other complex structures can be produced far more efficiently this way. As the engine evolved from Raptor 1 to Raptor 2 and now Raptor 3, manufacturing simplicity became a major priority. Raptor 2 was essentially a complete redesign, with fewer parts, fewer connections, and significantly more welding integrated directly into the structure. Components that once required bolts and flanges were replaced with permanently welded assemblies, reducing weight and eliminating potential failure points. Raptor 3 pushes that philosophy even further. Many pipes, sensors, and supporting systems have been moved inside the engine itself, creating a much cleaner design with far fewer external connections. Fewer parts mean fewer welds, fewer leaks, lower maintenance requirements, and ultimately a more reusable engine. And perhaps the most impressive manufacturing tool of all is something that barely existed in aerospace a couple of decades ago: 3D printing. SpaceX makes extensive use of metal additive manufacturing, building parts layer by layer directly from digital designs. Instead of cutting away material from a giant block, the company essentially grows components into existence. It's a little bit like science fiction, except it actually works. This allows engineers to create incredibly complex internal channels, cooling passages, and structures that traditional manufacturing simply couldn't produce. Critical components, such as injectors and turbopump elements, benefit enormously from this approach. The injector alone contains intricate pathways responsible for delivering fuel and oxidizer into the combustion chamber with extreme precision, while turbopump components must survive enormous temperatures, pressures, and rotational forces. The result is an engine that's lighter, stronger, more reliable, and easier to manufacture than its predecessors. While 3D printing is an incredible technology capable of producing extremely precise and complex components, not every part of SpaceX's Raptor engine can be manufactured this way. The main limitation is cost. Although 3D printing excels at prototyping and small batch production, expenses can escalate rapidly when scaled for mass production. As a result, many Raptor engine components still need to be made using more traditional manufacturing techniques. In many ways, Starship's evolution tells the story of SpaceX itself. Early prototypes were rough, sometimes messy, and occasionally exploded spectacularly. But each failure revealed weaknesses, and each weakness led to improvements. The welding process followed that same path. Today, those cleaner weld lines aren't just cosmetic. They're visible proof of thousands of lessons learned, countless design iterations, and SpaceX's relentless obsession with turning a giant stainless steel rocket into a vehicle capable of flying to the moon, Mars, and beyond.